Hi BHS, welcome to part 4 of our Unit 4 discussion on atomic structure and history. The student expectations are the same 3 that we've had for every other video in this series, so rather than read them out to you, let's jump right into the notes. Okay, when you need to find out what is inside of an atom, there are a couple different things you need to consider. First of all, you need to consider atomic number. Atomic number is the number of protons that are inside that atom's nucleus. You can find the atomic number for any element by looking at the periodic table. The elements in the periodic table are listed out by element, by atomic number. So if nitrogen has the atomic number of 7, that tells you that every nitrogen atom has 7 protons in its nucleus. The mass number, or atomic mass number, tells you what the total number of particles are inside the nucleus. So it's the protons plus the neutrons. This is not the same thing as the average mass that you find on the periodic table. That we'll talk more about where that comes from later. Just going back over some of the parts of the atom. Remember, the nucleus of the atom is in the center. It's where the protons and neutrons and the bulk of an atom's mass are kept. And then you've got electrons moving around the nucleus. Now, this is the planetary model, if you remember from our last video. We now know that electrons don't orbit the nucleus like a planet around a star. So I want you to start getting rid of the idea of an orbit. Okay? Start to blot that out of your mind. I want you to think in terms of shells or in terms of energy levels. Look at a few example atoms here. Hydrogen is element number 1. So for hydrogen, its Z is going to be equal to 1. That tells you that it has 1 proton in its nucleus. And see, there it is right there. Now, the total number of particles in its nucleus is 1 because there are no neutrons. So for this one, its A would also equal 1. You take the total mass of the particles in there. You don't count electrons when you're looking at mass because compared to protons and neutrons, they have such a teeny tiny mass. Here's an atom of lithium. Okay, and you can tell here that lithium has 3 protons. That's because it's element number 3. So for lithium, its Z is going to be equal to 3. Now, its atomic mass here is going to be equal to protons plus neutrons, and so you count total particles. We got 1, 2, 3, 4, 5, 6, and 7. Has an atomic mass of 7. Now, if you were just given this information here and you had to find out how many neutrons this atom of lithium had, you take its atomic mass minus its atomic number. So 7 minus 3 would give you these 4. In a neutral atom, and it's very important that we talk about neutral atoms here. Neutral meaning they are not positive or negatively charged. They will have the same number of electrons that they do number of protons. So if the atomic number is 5, that tells you an atom has 5 protons. If it's neutral, it also has 5 electrons. Okay. Here's another example. Beryllium. It has 4 protons, so its atomic number Z would be equal to 4. Now here, this one has also 1, 2, 3, 4, 5 neutrons. So its total atomic mass, A, is going to be equal to this 5 plus the 4 protons, so its atomic mass is 9. Now, those were all neutral atoms. If you have an atom where it doesn't have the same number of protons and electrons, then it's what's called an ion. Okay? And yeah, the way it's put right here, your number of electrons is not equal to your number of protons. An ion isn't always just a single charged atom. Sometimes it can be a group of atoms that are treated as a single piece, as a single atom. Okay? But they've got a total positive or negative charge. If it's a positively charged atom, it's called a cation. A way that I remember that is because I'm a fan of cats, okay, and so I have very positive feelings about cats, okay? So here's the cat ion, here's his little ears, nose, whiskers. Okay, he says meow. Cation is a positively charged ion. And the reason that an atom becomes positively charged is if it loses one or more of its electrons. Okay, so its number of protons is going to be greater than its number of electrons. So here you've got a sodium atom. This sodium atom is neutral, 11 protons, 11 electrons. Here's a sodium ion. It's lost one of those electrons. Okay, I'm not sure how. Oh well. But you see now it's got one more proton than it does electrons, and so it has a total charge, 11 minus 10, has a total charge of plus 1. Okay, and you can see here it's marked with a little positive charge. An anion is an ion that has a negative charge. Now this is not pronounced anions, okay? There ain't no anions. It's an anion, and it's a negatively charged atom, okay? The way I like to think about this one is sometimes your parents annoy you because everywhere you go they're always keeping an eye on your business, okay? They're always texting saying, hey, where are you? When are you going to be home? What you doing? And it's not their fault, they're parents, that's what they're supposed to do. But it does sometimes get annoying that they always feel like they have to keep an eye on you, okay? You have negative feelings about your parents because they're always keeping an eye on. Okay? And it makes you mad. Here's an example. This chlorine atom is neutral. It has 17 protons and 17 electrons. But it gains another electron from somewhere. So now, you take 17 minus 18, you get a total charge of -1. It becomes a negative ion. Okay? Now I want you to notice something else too. Look at what happened to the radius of this atom of sodium when it lost that electron out of its electron cloud. It got a little bit smaller. This chlorine right here, when it gained an electron, it's now a little bit bigger around. Okay? So that's what happens. Whenever an atom ionizes, if it loses an electron, its total size shrinks. If it is gaining an electron, its total size from the nucleus out to the edge of the electrons gets bigger. Okay? Here's a boron ion. That's kind of fun to say. It has 7 electrons, 5 protons. So if you take a look here, protons 1, 2, 3, 4, 5 electrons. Here's the 2 that are in the inside, and then 1, 2, 3, 4, 5 more for a total of 7. Okay? So here you would do your 5 protons minus your 7 electrons, and it gives you a total charge of -2. Okay? So this has a -2 charge. Okay, I told you a minute ago that we were going to talk about where that average atomic mass came from, and here it is. Different atoms of the same element are called isotopes. Okay, this root iso is Greek for same. Sorry this is taking so long. I broke my little tablet when I was making this video, so I'm drawing stuff with a mouse. Okay, iso means same. So these are atoms of the same type. They have different numbers of neutrons, and because they have different numbers of neutrons, they have different masses. Here's 3 isotopes of hydrogen. The most common isotope of hydrogen is this guy right here. Okay, it's got a mass of 1 and a charge of, or I'm sorry, a atomic number of +1. This is what is called protium. No, I'm not going to write that in just in case it's already on there. Anyway, it's called protium. It's the most common form of hydrogen. This form of hydrogen right here has 1 proton, but it also has 1 neutron, so it has a total mass of 2. Okay? This is what's called deuterium. It's a little bit rarer, I think probably about 10% to 8% of all the hydrogen on the planet is this kind of hydrogen. And then very, very rare you run across this kind right here. This has 1 proton and 2 neutrons. Okay, so it has a total mass of 3. This is what's called tritium. Tritium is actually very, very radioactive. It's used as a triggering substance in nuclear weapons. If anybody saw Spider-Man 2, this was the stuff that Dr. Octopus was trying to get a hold of so that he could like do the whole nuclear fusion thing with his robot arms, which is a total load of baloney, but it made for a pretty fun movie. But all 3 of those are isotopes of hydrogen. Notice that the atomic number is the same for all 3. Okay? The atomic number doesn't change. The number of protons doesn't change. The only thing that changes is number of neutrons, and that also changes an atom's mass. This atom is twice as heavy as this one here, and this one is 3 times as heavy as this one here. Okay, so again, isotopes are atoms of the same element. They have different mass numbers. Okay, so take a look here at the atomic symbol. This right here tells me everything I need to know about this atom. It's an atom of carbon, and even if I didn't know that that was an atom of carbon, I could look right here at the atomic number, which is 6, and that would tell me it's got 6 protons, and only carbon has 6 protons. This 12 right here tells me about the mass of that atom, which in this case, this tells me how many neutrons I have, because I take this total mass 12 minus 6. That tells me I have 6 neutrons. Another way of saying it, instead of writing this out, would simply be to say carbon 12. Okay? And so you'll see something like this on the test. Okay, that's just that particular isotope. Oh, that's a pretty picture. Here's carbon 12, the most common form of carbon on the planet. Here's carbon 14, very, very rare. The difference between these two, take a look right here. Okay? 6 neutrons in carbon 12, 8 neutrons in carbon 14. Carbon 14 is special because carbon 14 is also radioactive. And that means that it's unstable, that pieces of the atom over time will fall off and it will change from carbon 14 into a different kind of atom. And that's one way that they can use to date really old fossils and things, is they see how much of them is carbon 14, because we living things are constantly replenishing our carbon supply from the food that we eat. So we're constantly taking in new carbon 12, carbon 14, and everything else. After we die, we stop taking this guy in, and over time it decays and it changes into a different kind of atom, and we can measure how much carbon 14 is left in what used to be a living thing to figure out how old it is. It's called radiocarbon dating. Okay, let's look at some examples. If I had an atom of chlorine 37, okay, my atomic number would be 17. How did I know that? I looked on the periodic table for chlorine. My mass number, I don't have to look at the periodic table because it gives it to me, oops, right here. Okay, I can get rid of that. Nope, doesn't look like it. Mass number is going to be 37. Number of protons I get from my atomic number. So number of protons is 17. There's a bug on me. Go away. Number of electrons, if this is a neutral atom, should be equal to my number of protons. And my number of neutrons, the way that I get that, remember, is I take... Can I erase? I'm totally going to erase now. Nope, won't let me do it. Never mind. I take my mass number, which is 37. I subtract 17 from it, so 37 minus 17 gives me 20. That tells me that out of that mass of 37, 20 of those have to be my neutrons. Okay? Here's the nuclear symbol. Mass number on top, atomic number on the bottom. And that's it.